No, it's that secret word that we talked about.
So we're going to learn Green's theorem. This is huge. It's one of my favorites.
Oh, well, we can't because I don't have.
Part of this reason why it's one of my favorite things is because when I was a senior in college, I went on a college trip. I went to Wabash College.
Wabash. I don't know how you pronounce that.
Wabash College is in Crawfordsville, Indiana. It's a really pretty good school.
My friend goes there.
But it's all boys.
Oh, too bad.
And I wouldn't want that.
Well, man, why would you want that?
Yeah, that's right. But I sat in on a Calc 3 class. It's so funny, whenever I went to colleges, I always wanted to sit in on that class. But I didn't go to college initially. But
ooh, it's like a foreshadowing.
But the class that I sat in on, the day I sat in on it, they learned Green's theorem. And I kind of followed along what they were doing. It just looked familiar.
Wait, what math class were you in?
Like BC. So this would have been November. So I mean, I would have just been learning about derivatives and integrals and stuff. So the other day, I learned you the divergence of a vector field. We said was del dot f. Did you guys watch that video?
No. What?
You probably want to watch that video.
What video? You put a video on Classroom.
Let me Google.
Yeah. I only remember because you said on the Google.
Oh, that's what you're talking about.
Okay. So the divergence is del dot f. Okay. And if f is a vector field in a plane, everything that we're going to be doing today is in a plane. Okay? If f is a vector field in a plane, the divergence of f equals the partial m with respect to x plus the partial n with respect to y. Okay? Now, we said the other day that calculation, okay, that's a number, right? That calculation gives you the tendency of the vector field at a point to be spreading out or compressing. Okay, remember that? Another thought about it, or another interpretation of it, is that this quantity is what we call the flux density per unit area. At a point. Okay, so what do we mean by that? So like you calculate that divergence at the point, and that's going to give you the amount of outward flow per unit area, per whatever area you're in, like meters squared, inches squared, whatever. It's going to be the flux density per unit area at that point. Okay? If flux is positive, it's outward. If flux is negative, it's inward. Okay? So if flux is outward, it's as if, like, at this point, if you have outward flux, it's as if there's like if we're talking about a fluid, it's as if the velocity just came out of, there was a source and just appeared out of nowhere and was flowing out. If the field was the velocity of a fluid and the flux is negative, it's like the fluid is compressing in.
Like draining?
Draining, right.
Wait, so positive is it
Outward.
down?
Yeah. Right? And the other quantity that we learned the other day was the curl of f. Okay? And we said that the curl of F is del cross F. Okay. Now, if we have a vector that's only in a plane, okay, when we have a vector that's in a plane, we don't have that z component, right? If our vector field is only in the xy plane, we've got no z. Okay. So in the plane, we typically will talk about, after you cross these two vectors, you get the z component, the kth component. In the plane, we typically will talk about the kth component. It's the kth.
So I was trying to think. I thought I was confused because I don't know what you get. Because I've crossed vectors before in a plane. I do that in physics, but I don't really know what that means. You get that key component. I didn't really get it.
It's we'll do one here in a second just to show you. Okay. I think we said this the other day. Curl F dot K. Yeah.
So it's del F.
It's del cross F dot K. And I'll show you what that means as soon as I say my next thing. Okay? I think we said the other day that the curl, okay, and particularly when we're in a plane, the curl is giving us a measure of how much rotation there is at a point.
Okay, that's
Okay?
right.
At a point. Okay? So if we're in a plane, in the xy plane, the rotation, the axis of rotation is going to be k straight up. Okay? The magnitude of that vector of the curl is actually going to equal twice the angular velocity. Okay, I think we said that. Okay?
So that's what the k vector means.
That's the k vector. It's like that axis of rotation.
But the magnitude of that.
The magnitude of the curl, and the magnitude of this vector, is going to be twice the angular velocity. Okay? Now that twice the angular velocity is not going to do a whole lot for us, but
So that's what it means.
but that is what it means. Positive rotation we're going to define to be counterclockwise, and negative we're going to define to be clockwise. So that's convention. Okay. But interestingly, is that this quantity, when I do curl F dot K, so let's go ahead and let's see what this looks like. If F equals M in the I plus N in the J plus 0 in the K. Yes? If I do del cross F, okay, I'm going to get I, J, K, partial X, partial Y, partial Z, M, N, Z, okay?
Wait, 0, that's a 0?
Yeah, because there's no K vector right here. If your field is in the plane. Okay, so compute that cross product for
I
me.
thought you randomly had used O instead of P.
Okay, compute that cross product. You ready? So here we go. The I component of that cross product is going to be the partial of Y of 0, which is 0, minus the partial N with respect to Z. Right? Minus J. The J component is going to be what? The partial with respect to X of 0, which is 0, minus the partial M with respect to Z. Yes?
Yes.
plus the k component is going to be the partial of n with respect to x minus the partial m with respect to y. Yep.
Oh, I see.
Now, if your vector field is only in the xy plane, what is this? 0. And what is this? 0. So you're really looking at partial n with respect to x minus partial m with respect to y in the k direction. Okay? Now, if I dot that with the vector k, I'm just going to get that right there, right? Because if I dot that vector 0, 0, this with the vector 0, 0, 1, I'm just going to get that quantity right there. So that quantity right there. Hold on. Hold on, I got you. Just let me write this down. Okay, that quantity right there. So remember, this says curl f dot k. Well, curl of f is the vector 0i plus 0j plus this k. And if I dot that with the vector k, which is 0, 0, 1, I'm just going to get that component. Okay? So this quantity right here, my friends, can also be thought of. You know, we said if this quantity is positive, we have counterclockwise rotation. 2 times this quantity is the angular, or this quantity equals 2 times the angular velocity of the rotation. Okay? But you can also think of this as what we call the circulation density. Density? Yeah. The circulation density per unit area, okay, at a point. Okay?
So it's after you thought of K, then you have the circulation
Yeah.
density.
So if you look at these two quantities, this guy right here and this guy right here, okay, they're very similar looking, right? They're not the same, obviously, but they're similar. The top one, hey. Dispenser. It's for all testing stuff, yeah. Spencer, Kessner, yeah, those guys. Neither one. Yeah. I mean, I don't know if it matters. One of the other. Wow. I can't believe that's. If I had more time, I would. There's a lot of stuff there that we bought that we probably didn't use. That stuff's in a crate. We didn't lose 1,200 washcloths. So, yeah. Well, okay. Well, and I didn't buy that stuff. I mean, well, maybe I did. Yeah, probably. Yeah, ask Spencer. I don't know. Yeah. I don't know. I mean, it's private testing, but that's where they keep all the testing stuff. In East. I don't know. All right. Well, then, let me know. No, I definitely won't. I don't have any room for it. I mean, okay, thanks. Bye.
What is that mean? What about your washcloth, man? They okay?
So,
Oh.
yeah. So both of those quantities look very similar, right?
Yep.
Like,
Yeah.
you know, this one, but they're vastly different. This one here is essentially the flux density per unit area, how much we're spreading out or spreading in at every point. This one is telling us how much rotation there is at that point. Okay? Does that make sense? So now, how's this stuff connected to line items? Well,
Can you talk about both of those things with, like
what do you mean?
what would this circulation look like?
So, if the divergence, positive divergence on a vector field is out like a source, like outward flow at a point. It's like the water, the fluid just springs into existence. Negative divergence means that the at that point the fluid is compressing, sinking in. Okay. This one, when you do this calculation here and you get a positive number, there's a positive amount of rotation that's happening there. And the speed of that rotation I'm going to say it's easier to say it the other way. This calculation is twice the angular velocity. Okay. If this is negative, it's counterclockwise. Sorry, clockwise. Did I say counterclockwise the first time? I think
no,
I
the first time you said
clockwise. Clockwise is negative. Counterclockwise is positive. Okay. It goes kind of against what you want it to be. You want counter to be negative, but it's positive. Okay. If this quantity is 0, there's no rotation at all. Okay. So the only one that we're talking about, like sinks and sources, is more of this here. Okay. So how is this connected to line integrals? Well, it's Green's theorem. So what does Green's theorem say? Well, there are two forms of Green's theorem. Okay, so we're still talking about Green's theorem in a plane. Okay, Green's theorem actually only exists in a plane. Because when you move out of the plane, Green's theorem actually becomes named something else, which we'll get to in eventually. Theorem, yeah. Okay, so here's going to be our conditions. We're going to say let's let F be like what it was over here. M in the I plus N in the J, okay? And C, which is going to be a curve, is going to be a closed, smooth curve, okay? So we have two forms of Green's theorem. We have Green's theorem for flux, and we have Green's theorem for circulation. So Green's theorem for flux. I'm going to try something. The way I state this, and see if you guys can come up with it. Do you remember this? What's that? It's one side. Yeah. And when we learned that, what did we say that equals? The F of B minus F of A. Okay? But kind of more deeply, what is it that we're doing when we integrate F prime? We're saying the sum of all of the changes in x per unit x over this interval from x equals a to x equals b. The sum of f prime, the sum of dy dx times dx, it actually equals the change in f along the edge of the interval. We even said when you integrate a rate of change, you get the change in the quantity. It's the net change in the quantity. Right? Does that make sense?
Yeah.
So what would happen if I did this? So here's curve C. Okay. Our vector field's in here. Draw. Oh. Sorry, Kate. Our vector field's here. Oops. Our vector field's in here. Our vector field's in here. Whatever. Okay. Explain to me this integral. What is it? Yeah, you're adding up some stuff. But what is it that you're adding up? Yeah, you were so close. And you're telling me what it's going to equal. Okay? Before we get to what it's going to equal, just tell me what it is. What are you adding up here? You're adding up the flux density per unit area at every single point in here. That's what you're adding up. And you're doing it over the whole area. Right? So what's that going to equal? It's going to equal the net change in flux along the boundary. Oh. Okay? Because this right here was a net change in f along the boundary. It's just the boundary was a very stupid boundary. It was 2 endpoints.
So this is just around the edge?
So this is going to equal the net change in flux along the boundary, which that's what we already learned. Right, you just said flux density. You said net change in flux density. Okay? Because we learned this right here. We learned how to compute this as the sum of all the fluxes along the edge of the region, right? That's what we learned. Okay? This is the net flux. Okay? That's what that is. It's the net flux along the total edge. Remember what this is? What are we summing up here? We're summing up all of the tangential components of F along that boundary. Okay? But now we've got these things connected. This integral right here, which is a line integral, we have that connected to a double integral. Okay? But remember, what is it that this is summing up? You're summing up the flux density per unit area over, or you're summing, another way of thinking, you're summing up the rate of change of flux per unit area over the whole area. And what does that equal? The net flux along the boundary. The change in flux along the boundary. Wow, that's pretty heavy, okay? What's the other form? The other form is circulation. Okay? By the way, the flux typically we refer to as the normal form of Green's theorem. Oh, by the way, before we do circulation, I want to write down one of the things because we didn't write this. Because we remember we had another way of writing this, which you guys didn't like as much, but we had another way of writing that. These two were analogous. Okay, but they both equal this. Okay? So then circulation, the other form of Green's theorem, which we'll say is the tangential form, says this. And guys, I'm actually stating these theorems to you in a reverse way that they're typically stated in a book. But we're stating them in a way that's conceptually equivalent to the fundamental theorem of calculus. Because if you think about what you're doing is adding up rates of change over some region, it's equal to the change in F along the boundary. Okay? So what's this going to equal? Or well, that's before we say what it equals. What are we adding up? Here, we're adding up the circulation density per unit area. And we're adding that up over the whole area. And what's that going to equal? Still doing it inside the area. So we're still this side right here, we haven't written what it's equal to. What this calculation is telling us is the sum of all of the circulations per unit area, the sum of the rate of change of circulation per unit area over the whole area. What's it equal to? It's equal to the net circulation along the edge. Okay? Because remember, when we said, what did you have for me? Snacks. We're recording.
Wait to yourself. Don't for the camera and wait to yourself.
Because remember, when we learned about F.dr and F.tds, we said that if the path was closed, that was called circulation. Okay? So, F.tds, remember, is also the same thing as this, F.dr. It's the tangential component. And what is it in line integral form? Or differential form, I mean. this form here. Do you remember?
Wait, I didn't miss this.
Well, these two are equivalent, yes? Okay, these two are equivalent. What's the third way of representing that? M dx plus n dy. Okay? So we got, these are two major things here. Like, because you've got two ways of looking at the fundamental theorem of calculus in a completely different way. But if you think about what is it that you're adding up here? Kate, I wouldn't try to copy this down now because it's gonna look like greedy. Okay, if you think about what it is that you're adding up here, okay, you're adding up all of the rates of change of flux per unit area over the whole area. So you're adding up all of the flux inside, the rate of change of flux along the inside. And what does that equal? It equals the change in flux along the boundary. Okay?
Okay, I'm trying to figure out why. Would it cancel out sort of like the flux is on the inside of the area? Does that make any sense?
Yeah.
Yeah?
I mean, it's kind of like, why here? You know? Like, why is it that if I add up all of if I'm going from here to here, and I add up all of the velocities of myself from here to here, and I multiply that by a little tiny, just infinitely small distance, and I do that an infinite times over the whole, why does that equal just the change in my position? Like, because velocity is the rate of change of position, right? Why does that work? Like, I mean, that's huge. That's a big question. I mean, we have proved in this theorem. The old fundamental theorem, we could sort of prove with kind of rectangles.
So it's not proven.
Oh no, it is. It's
Yeah.
just we haven't done it and we won't. I think it's more important for us at this point, rather than to prove that, to understand what it says. Like that, that essentially, if I wanted to find the flux of this field across this path, it's equivalent to finding the total it's equivalent to finding the summing up all of the flux density of the area there over that whole area on the inside. Okay. Or conversely, if I wanted to find the circulation of this field along this path, it's actually equivalent to doing this calculation right here. But both of those are equivalent to, they're just higher dimensional forms of this. Because this right here is you're summing up the rate of change of f per x over some interval, some x interval. And what did it equal? The change in f along the edge. That's what these are. It's the change in flux along the edge. It's the change in circulation along the edge. Right? Now, what this is going to look like when we move it into space is now we just won't be talking about a curve. We'll be just talking about a surface.
Wait a minute. That kind of like.
And we're going to do the exact same thing again. And these two forms of this theorem will just become two new theorems that deal with the same idea in space.
Wait, real quick though. So if you have a ball rolling down a hill and you want to measure its, kinetic energy, you have to add as two components, the velocity of the actual thing moving forward and the angular velocity of the spinning. I kind of think of them as separate things. That kind of looks like this. So like
acceleration is the rotation.
Right.
Flux is coming through. I mean, or going out.
The amount coming through.
Yeah.
That's like,
So tomorrow, I guess we'll have to knock out some examples of this. So Kate, you want me to email? You want me to just put this on the Google?